Hey, welcome to The Explainer. Today, we're diving into a topic that can sound a little intimidating, but it's absolutely crucial for building modern software: Java multithreading. And we're going to kick things off with a problem that, well, I guarantee you've run into it.
Oh, you know the feeling. You click a button, maybe to save a big file or run a report, and boom, everything just stops. The little spinning wheel of doom appears, the whole app grays out, and you can't click on anything. It's super frustrating, right?
So, that frozen screen, it's not just some random glitch. It's actually a symptom of a much deeper problem and how the app is designed to do its work. But the great news is there's a really elegant fix, and we're going to break it all down today.
See, the real issue here is that a simple application can only do one single thing at a time. So when you give it a really heavy job to do, it pours all of its energy into that one task. And that means everything else, including the very user interface you're trying to click on, just gets completely frozen.
So what's the solution? Well, you hire more help. And that right there is the whole idea behind multithreading. Instead of having one poor, overworked person trying to juggle everything, you bring in a team of background workers, we call them threads, to handle different jobs at the same time. This keeps your main application totally free and responsive.
Okay, let's really nail this down with an analogy. Think of it like this. Your entire application, say your web browser, is like a house. That's the process. It's its own building with its own address and its own private resources. Now, a thread is a worker inside that house. The great thing is you can have lots of workers in the house, and they can all cooperate because they share the main space and resources, like the kitchen, or in our case, the main memory.
So why does this matter so much? Look, beyond just keeping your app from freezing, this is all about raw, pure efficiency. Pretty much every computer now has a CPU with multiple cores, and a single-threaded app is just leaving all that power on the table. Multithreading lets you use all those cores, which is exactly why it's the backbone of everything from massive web servers to fast-paced video games to huge data analysis jobs.
All right, so we've got the what and the why down. So now let's get our hands dirty and look at the how. We're going to check out the modern and honestly the best way to actually create and run these threads in Java. So the best practice today uses what's called the runnable interface. The big idea here is brilliant. You separate the task from the worker. The runnable is like the to-do list. It just defines what work needs to be done. The thread is the worker you hire to actually do it. And this is awesome because it gives you so much flexibility. You can define a task once and then hand it off to as many workers as you want.
And in modern Java, oh man, this gets so clean. Since runnable really only has one job to do, you can use a slick little lambda expression to define the task right inside the thread creation. I mean, just look at that. How elegant is that? That one line defines a task and kicks off a brand new worker to get it done.
Okay, now listen up, because this is the golden rule. This is the one mistake everybody makes at first. You absolutely must call the .start method. Calling .start tells the system, hey, create a new worker and give it this job. If you accidentally call .run yourself, you get zero multithreading. Zilch, nada. You're just running the code on your main thread, which totally defeats the whole purpose and brings you right back to that frozen app problem.
Okay, so we've hired our workers. They're all doing their thing. Our app is super responsive. Awesome, right? But what happens when two of those workers try to grab the same tool at the exact same time? Well, that's when things can get messy. It's a race to total chaos.
This, my friends, brings us to the villain of our story, the race condition. This is a nasty kind of bug that pops up when multiple threads are all trying to read and write to the same piece of data. The final result becomes completely unpredictable, depending on which thread gets there first. It's a recipe for disaster and corrupted data.
Let's walk through exactly how this nightmare happens, step by step. Let's say we have a shared counter, and its value is 0. First, thread A comes along and reads the value. It sees 0. But before it can do anything else, the system pauses it and lets thread B have a turn. So thread B also reads the value, and it also sees 0. Now thread A finally wakes up, adds 1 to the 0 it read, and writes back a 1. Then thread B wakes up, does its math on the 0 it read, and it also writes back a 1.
And the final count? It's 1. We did the work twice, but we only got credit for it once. An entire operation just vanished into thin air. Our data is just wrong. That is a classic and very dangerous race condition.
So how do we fix this? How do we stop this chaos and get our workers to cooperate? It turns out we just need a rule, a really simple but super powerful rule.
One at a time, please.
And the fix comes down to one single, almost magical keyword in Java: synchronized. By just adding this one word to our method declaration, we put a lock on it. This lock enforces our one-at-a-time rule. Look at that. Just one word, and we've solved this huge, dangerous problem.
So what's the magic here? How does this actually work? Well, every single object in Java has a secret built-in lock. To run a synchronized method, a thread has to get permission. It has to grab that object's lock first. And while it's holding that lock, any other thread that shows up and wants to run that same method gets stopped at the door. They're blocked. They have to wait in line. As soon as the first thread finishes, it releases the lock, and the next thread in line gets to go. It guarantees our operations don't get mixed up.
All right, so let's boil this all down. What are the big takeaways here? First, threads are your background workers, and they're the key to a responsive app. Second, use runnable to define the jobs. It keeps your code clean. Third, and this is the big one, always call .start. Never, ever, ever call .run directly. And finally, when your workers have to share data, you absolutely must use synchronize to keep things orderly and prevent chaos.
And that leaves us with one last, really interesting question. If synchronized is this amazing fix that prevents all this chaos, why don't we just slap it on every single method and call it a day? I mean, what's the catch? What could possibly be the downside of just having our workers always politely wait their turn for everything? And that question, well, that's where things get even more interesting. Thanks for joining us on The Explainer.